reason it's important to understand what the derivative represents is because, like I said, we can throw it into sort of different sections in the sense that, particularly with functions, we do throw it into inequality questions. You would have seen that if you've been going through past papers. And so if we don't know what it means, then it does become harder to deal with. Okay, so like I said, it's the instantaneous rate of change at a specific point. So instantaneous, instant at a specific point, which essentially means gradient. And this allows us to do a whole bunch of things. So we can work with tangent lines. We can work with turning points or stationary points. Be a better terminology, stationary points. Obviously, when we get into second derivatives, we start talking about points of inflection. There's a whole bunch of stuff we can now work with. Obviously, concavity. So there's a lot that a derivative can do for us in terms of, particularly when we start talking about functions. Excuse me. But like I said, when we start working with a derivative, it allows us to do a whole bunch of things. So then it's great that the derivative allows us to do all of this, but how do we find the derivative? So there's two general ways that we need to know. The first way that we need to be able to find the derivative is using first principles. Now remember, this formula is on your formula sheet, so it's not one you need to remember, but obviously you do need to know how to work with it, and we'll chat about that just now. So first principles formula, f prime x, or the derivative of f, is where your limit tends towards h is to 0 of f of x plus h minus f of x all over h. Okay, and we've done a whole bunch of first principle questions, so that's nothing new or nothing unknown. And as I've said to you, you're always going to get a first principles question, so you can guarantee that it's going to happen. And they're generally anywhere between 4 and 6 marks, so it's a decent chunk of marks, so you need to be able to apply your first principles. The second way that we can find the derivative is using our rules. Okay, so your rules essentially tell us that if we have an expression, and I'm going to use variables here of, say, for example, a x to the power n plus some sort of constant, when we find the derivative of that, we take the exponent and multiply it by the coefficient, so n times a, and then we take that exponent and subtract 1, and any constant derives to 0. Okay, so this is sort of the little rule that we've learned in terms of how to shortcut first principles and find our derivative. Now again, anytime you're finding the derivative, I would use the rules unless you are specifically told calculate the derivative using first principles. If you're not told to use first principles, just use the shortcuts, okay? No point in going through all of those steps of first principles if you can just use the shortcut. Just in terms of your rules, there's a few things that we need to bear in mind. Our formatting is obviously really important when we are working out derivatives. So first thing, or a few things that we need to remember, is that we never want a variable in the denominator. If there is a variable in your denominator, you need to introduce a negative exponent. All right, so that's the first thing. The second thing in terms of our formatting that we need to remember is we don't want any roots, so no surds. If there is a root, so let's say, for example, you've got the square root of x, you need to change that to a rational exponent. So power half or whatever. And then the final thing that we need to remember in terms of our formatting is that we always must simplify. So whether that means whether that means adding like terms, factorizing, and then simplifying a fraction, whatever the case may be, we always want to be working with the simplest form of the expression before we go and find, excuse me, the derivative. Okay, so that's just some things that we need to remember when we are finding the derivative. And again, like I say, Once you've answered your first principles question, you're going to get questions that test your application of both formatting and derivative rules. So you need to be able to do these things. Sorry guys, I've got such a frog in my throat. Right, the next thing that we need to be able to work with is cubic functions. So I'm just going to wait here in case you want to screenshot any of that information. And then I'm going to move on to just summarizing some cubic function stuff. Okay, so cubic functions, generally speaking, you need to be able to work with a cubic function, but you also need to be able to draw a cubic function. Now, in terms of drawing cubic functions, it is much like any other function that we've drawn. You need to show important points. Those important points being the stationary points, or your turning points, your x-intercepts, your y-intercepts. You only ever show point of inflection if we ask you to. Okay, so just a few things about your cubic functions. If A is positive, you will get a cubic function that essentially increases, decreases, increases. Terrible cubic function, but you get the picture. And if A is negative, you get a cubic function that decreases, increases, decreases. Now. So decreases, increases, decreases. Based on that, obviously, you can then work with gradients again. You can then see your tangent lines where they would have a positive or negative gradient, etc., etc. Right, your cubic function has a general or standard form of ax cubed plus bx squared plus cx plus d. And we need to also be able to factorize cubic expressions. Now, we've spoken about two methods. We spoke about synthetic division as well as just factorizing a cubic using remainder theorem. I've said to you guys before, I don't really care which one you use. The markers don't care which one you use. As long as you can factorize a cubic, you do. Okay, so like I said earlier, cubic functions, yes, are algebraic functions, but we rely quite heavily on the derivative in order to work with cubic functions. So this is where the derivative comes into play, and we have two derivatives that we can work with. The first derivative, as I've already explained to you right at the start, gives us information about the gradient of our tangent. All right, so that's not what I wanted to do, so let's try that again. If your first derivative is positive, so if it's greater than 0, this implies that our graph is increasing. If our first derivative is less than 0, this implies that our graph is decreasing. And if our first derivative is equal to 0, we are now talking about our stationary points. Right, so if we go up to these little cubic functions here, oh, sorry. So if we talk about where our graph is increasing, always read your graph left to right. So that is increasing, this arm is increasing, and then for your negative function from turning point or stationary point to station point, we're increasing. In terms of where your graph is then decreasing. For positive cubic, it's sort of the middle section between stationary points. For a negative, it's sort of the two ends of your cubic function. And as we said, if f of x is equal to 0, you have stationary points. So you have essentially your turning points. All right, and that's what the first derivative essentially does for us. This helps us work with tangent lines. So if we're looking for the equation of a tangent to a cubic function, this is where we will use our first derivative. Obviously, we'll also use our first derivative when we're looking for our stationary points. Right, we then have the second derivative, and the second derivative now comes in terms of concavity, so where the position of your tangent line changes. All right, so once again, if your second derivative is positive or greater than 0, you have a concave up situation. I will explain concavity again if we're not too sure. If our second derivative is less than 0, we have a situation where we are concave down. And when our second derivative is equal to 0, we are looking at the point of inflection, which I mentioned earlier. Right, so if we just understand what concavity and points of inflection are very quickly. Right, so we've got a cubic function. Not the best cubic function I've ever drawn in the world, but it's okay. You get the picture. Oh, sorry. Just want to move that. Okay. Right, so I'm going to start with point of inflection, just because hopefully it's then going to make concavity be a little bit more logical. But your point of inflection, remember, is the point where concavity changes. And concavity is essentially, like I say, the positioning of tangent lines. That's how we can sort of view concavity. So if we go and have a look at, doesn't really matter which one we start with. So let's start with concave up. So in my mind, concave up is always the happy face portion of my cubic function. So this would be all the graph here on the right-hand side. And if you have a look, all of your tangent lines would sit somewhere along here for our concave up portion. It's all sitting below the graph. If we then talk about a concave down situation, the positioning of your tangent lines in terms of above or below your function changes. So now we can see concave down, all of my tangent lines would be sitting above my cubic functions. That point of inflection is the moment where it swaps over. Okay, so that's what concavity essentially means. It's sort of the positioning of your tangent line on your curve, and the point of inflection is there where that position changes from above the curve to below the curve. All right. Sorry. In terms of, now this is not something that comes up a whole lot, but I wanted to just raise it because every now and then it does pop up in a question, and it would be really silly for us to get it wrong if we were faced with it. Kani, what do you mean? Please explain stationary points, like what they are. Okay, cool. So a stationary point is basically a turning point. So if we go back up to these graphs here, the stationary points is where the curve turns, essentially. So you can call them turning points if you want to. Most textbooks and like exams and stuff refer to them as stationary points, but basically it's a turning point. Stationary because at that point, your gradient would be equal to 0. So it's a horizontal line. There's no rate of change at that specific point. Hence why it's equal to 0 in terms of your first derivative. So a stationary point is just a turning point. It's where your first derivative is equal to 0. And like I say, that's then because there's no rate of change there. The tangent line would be a horizontal, so there's no gradient. The gradient is 0. And so it's a stationary point. Does that make a bit more sense? Cool. Okay, sorry, I thought I said those words, but obviously I did not. All right, so like I said, this next little bit doesn't come up often, but obviously it's worthwhile knowing because it can pop up, and rather know it than not. Every now and then, again, not often, but every now and then, we have a situation where our turning points or our stationary points are the same point as your point of inflection. And basically what that means is that at that point, we change from a situation of, even concave up to concave down, but almost instantaneously. So let me draw the graph and then hopefully it'll make a bit more sense. So we can have a situation once again where A is positive. So it's increasing, and basically your graph would look something like that. It almost looks like a bit of a tan graph arm, or A is negative. And this would then decrease from left to right. And basically what this cubic function is that it doesn't have a changing gradient. So like the cubic functions that we're kind of traditionally used to, there's very clearly an increasing, decreasing, increasing portion of my cubic function. When your turning point or your stationary point is the point of inflection, the graph's gradient doesn't actually change. If A is positive, it stays a positive graph. If A is negative, it stays a negative graph. Essentially, that point of inflection and your stationary points are equal. And so concavity changes in terms of the positioning of your tangent line, which we can see quite clearly sits above and then sits below. But there is no change in gradient of your cubic function. Now, like I say, this doesn't happen very often, but it can pop up. So rather know the shape and kind of understand what it means than be blindsided by it. So this situation essentially means there's no local maxima. If I said no here, no local maxima or minima, but that point of inflection just indicates the change in concavity. Or again, not often, but it can. Okay, let's just get rid of that weirdness. Alrighty, so like I say, in terms of your cubic functions, this is sort of what we need to understand, know, and how to use the derivative with these functions. Like I say, the derivative is particularly useful with cubic functions. Obviously, you can apply the derivative to like quadratic. So if you really wanted to, you could use the first derivative to work out the turning point of a parabola. That's fine. There's nothing wrong with that. And you would use exactly the same method as we do here. So you would make your first derivative equal to 0. So there are definitely applications outside of cubic functions for these things, but we use them mostly when we talk about cubic functions. Right, again, I'm just going to wait here for you to take a screenshot if you want, and then we will have a look at derivative functions and then hopefully get into some examples. And obviously, if you have questions, just let me know. You can put them on the chat as you saw. I can see your questions come up and I will answer. All right, so in terms of derivative functions, the way I'm going to explain this is to try and draw all of these functions in a row. We'll see how we go. All right, now derivative functions is basically, if you were to find the derivative of a cubic function, you would end up with a quadratic function. The derivative of a quadratic function, you would end up with a straight line, etc., etc. Terrible straight line. And essentially, certain points on these derivative functions give us certain pieces of information about either the original graph or about the graph itself. Okay. I've not evenly spaced the situation out, but it's fine. We roll. I also don't want this here. Okay, so first things first, we have our cubic function. Again, you could just work with quadratic to straight line, but let's just go with this. So here's my cubic function. Again, I'm sorry, it's not the most beautiful cubic function you've ever seen in your life, but you're going to be fine. Our cubic function, we know, has got its stationary points. And those stationary points is where your first derivative is equal to 0. Okay. These stationary points, when we sort of translate that over to our derivative graph, okay, it's not going to be the straightest line in the world, but hopefully you're going to get the picture. Translate to the x-intercepts of my quadratic function. So if you are given a quadratic function and told it is a derivative graph, so it's the derivative of a cubic, wherever you see the x-intercepts, you know those are the x coordinates for your turning points or your stationary points. Okay, so there's my quadratic function, terrible quadratic, but again, we get the picture. So this is our original graph, this is our derivative graph. So I'm going to say it again. The x-intercepts line up with or have the same x values as your turning points or your stationary points. So like I said, I could tell you, here's the graph of f of x, and its x-intercepts are at 1 and, I don't know, 5. That would mean if you were to draw your cubic, you would have turning points at x equals 1 and at x equals 5. And you could then potentially draw your cubic function. So your x-intercepts and your stationary points of your original function, they match up in terms of their x values. Right, we also know that on a cubic function, we have a point of inflection. Right, our point of inflection, as we all know, is where our second derivative is equal to 0. And this point of inflection lines up with the turning point of your derivative graph. So again, the point of inflection's x value lines up with the x value of the turning point of your quadratic function. So if you knew where the point of inflection is, you knew where the x value of your turning point is. And then finally, if you wanted to find the derivative of your derivative function, so essentially a second derivative graph, you end up with a straight line. Now here, the x-intercept of your straight line matches up with your point of inflection and turning point of the first derivative graph. And so once again, if you know where the x-intercept of your straight line is, you know the turning point of your quadratic and hence the point of inflection of your cubic. So these x values all match up with each other and they help us understand what's happening if we were given a derivative graph. Right, the actual shape of your graph also is determined through derivatives. So we either have increasing portions of our graph, or we have decreasing portions of our graph. Right, so if we go back to the cubic, I can't remember what colors I used, so we're just going to go over like this. So increasing. An increasing part of my graph, remember again, you always read your graphs left to right if you want to figure out whether or not they have a positive or negative gradient. So this graph is increasing, then decreasing, then increasing. And obviously then what's in between is decreasing. So this is all decreasing. Now remember I said to you, your derivative represents your gradient. So when we get to our derivative function f dash x or f prime x, we need to represent this. Now remember, this represents the gradient. So your y values represent your gradient. So this is where y is positive. So this is where we have a positive gradient. Down here at the bottom, let's do this. This is where y is negative. So this is where we have a negative gradient. So the portions of your quadratic function represent where your graph is decreasing and where your graph is increasing. Now, if you look at this derivative function, this kind of makes sense, okay? According to my cubic function, my graph is decreasing between the two stationary points. We know that those stationary points' x values translate to the x-intercepts, and we can see that it's negative between the x-intercepts. So the increasing, decreasing sort of translates directly onto my function there. When it then comes to your straight line, essentially we're talking about concavity, okay? Because remember, second derivative, concavity. That wasn't the second derivative, was that? That was just two f's. So here we're talking second derivative, so we're talking concavity. Remember we said, so this is where y is positive, this is where y is negative. If your concavity is positive, it means it's concave up. If your concavity is negative, it is concave down. Down. Right, so if we go back up to our cubic function, I know there's a lot of colors going on, but hopefully it's all kind of linking up. This part of my graph, concave down. This part of my straight line, negative, concave down. And remember, the point of inflection matches up with that x-intercept on the straight line. Next part of my graph, oopsie, sorry. Apparently I'm opening a thesaurus, which is completely not useful to us. But anywho, this part of my graph, concave up, it's a happy face. This part of my straight line, concave up, it's a positive gradient. So derivative functions can give us a lot of information about our original function if we sort of know what we're looking for. So this was concave up. Hopefully we understand what I'm trying to say. So concave up and concave down. Right, usually we work more with the parabola, so the first derivative and original graph, rather than the second derivative graph. I'm not saying it can't be asked. It has been asked before. So you definitely still need to understand the straight line relationship. But generally speaking, it is between f of x and f prime x, so the first derivative and the original function. Like I say, the straight line has come up before, so expect it and understand it, but it definitely is more the second derivative function. Okay, I'm just going to wait here for you to screenshot, and obviously questions, let me know, Lorato.
Hi, ma'am. So, ma'am, if the graph was like first decreasing, then increasing, would it now the parabola be like a frown? And
Yes,
then
exactly.
the linear graph would be like sort of the other way around.
Exactly. So if we...
So going down, basically. Okay.
Exactly. So I can quickly draw that. I'm not going to do all the colors, but whoops. So essentially the question is if your cubic was negative. So I've drawn a positive cubic here. What happens if it was a negative cubic? So a similar sort of situation. There's my cubic, terrible cubic, but whatever. Your graph now starts by decreasing. So negative gradient, positive gradient, negative gradient, still with these x values of your turning points matching up with your x-intercepts. I know this is a terrible drawing, but you get the picture. And your point of inflection matching up with your turning point. And then, as Lorato said, your straight line now would be a decreasing function. Terrible. And again, x-intercept matching up with your point of inflection, because you go from concave up, positive, to concave down, negative. So it also applies your graphs just essentially reflect. Okay, so again, I'll just wait in case you do want to screenshot it with the negatives.
Okay, ma'am. And then I do have another question. So how would it basically, do we apply the same technique when translating it from a cubic to a parabola? Like if it went through the y-axis, maybe let's say like the increasing is by the left side, by the negative x-axis, and then...
So the x values aren't really like directly translatable. It's more the y values. When we then get to the, it's more the x values. When it comes to the y values, it's more where is it positive, where it's negative. So showing the gradient rather than whether it's on the positive or the negative side of the x-axis. But for example, so if let's say, for example, you had a cubic where you had a turning point here and another turning point here, when you draw your quadratic, this turning point and that turning point must match up. So you would have a quadratic that looks something like that, so that your x-intercepts match up like that. Okay. Leila, I saw your hand as well.
No, ma'am, I was gonna ask something similar to what Lorato said, but anyways, yeah, I wanted to ask: is it more likely that we're gonna get a positive cubic function or a negative one?
I reckon they're probably both equally likely, if I'm being honest. Maybe slightly more likely positive, but pretty much even.
Okay, thank you, ma'am.
Sure. Alrighty, guys. So that is sort of like the really important stuff in terms of calculus. I have put a little optimization section here, but realistically, optimization is the smallest part of calculus. So just very briefly, your measurement formula are NB, measurement. So knowing how to work out the volume of a cone the surface area of a sphere, all of that sort of stuff. We do give you the formulas, but obviously it's no good me giving you a formula if you don't recognize the formula. So I'm not saying learn them off by heart, but do be able to recognize your formulae. These formula, I know I say this to you guys, we often kind of neglect measurement, which is very much true. Any like grade 10 textbook, you should be able to find these formulae, and they should be listed in your grade 12 textbook as part of optimization and calculus. And then obviously just remember, optimization will ask you to maximize a volume, minimize a surface area, maximize. And when we ask you to do that, essentially what we're asking you to do is to find your first derivative and make it equal to 0. Find your x value and then potentially substitute it back in. So you're just working with first derivative equal to 0 and you go from there. Okay, but like I said, optimization, smallest part of calculus, not something I'm going to spend too much time on. Right, what I am going to sort of make a point of is in terms of the questions that you can expect. I've already gone through some of these. Excuse me. You're going to be asked first principles question, 4 to 6 marks. Make sure you can use first principles. You're going to be asked to determine the derivative, whereby you're examined on the formatting and the application of the rules. No, both. So there's it all there. You're going to be asked something on a cubic function. Other times it's relatively straightforward questions like maybe x-intercepts, stationary points, point of inflection sort of stuff. And then to potentially sketch your cubic function. Sometimes these cubic functions are combined with a derivative function, or you're asked something about the derivative function. And like I say, that has now been broken down for you. And remember what each derivative tells you. So like I say, first derivative is gradient. Where is it increasing? Where is it decreasing? Where are your stationary points? Second derivative is concavity and points of inflection. And then you will get an optimization question. Optimization questions, generally, like I say, the smallest of the section. Calculus is 35 marks, about 35 marks. Optimization maybe about a fifth of those marks. Okay, so realistically, not the bulk. Okay, we should be focusing on the other stuff. Tinswalo? Tinswalo, you there? Oh, there we go.
I didn't have a question. I think I just pressed it by mistake.
Oh, no, that's okay. Alrighty, guys. So, like I said, those are your types of questions that you need to be comfortable with. Like I said, optimization, if you know that calculus maybe is not your strongest point, or even that optimization is not your strongest point, that's not the end of the world. Okay, like I said, it's maybe 7, 9 marks. It's okay. You do your best, and then you go from there. Right, but it is the other stuff that we need to know. So I'm just going to wait in case you want to screenshot all of this, and then we're going to have a look at some questions. We do still have Wednesday for calculus, so don't stress if we don't get through everything, and if we don't get to all of these types of questions, it's okay. We will get there. Alrighty, so let's see what we have. So first question is asking us first principles. Again, you just need to know how to do this. Okay, the expectation is that you know your formula, you know how to apply it. And that's it. So like I said, first principles question, 5 to 6 marks, generally 5 marks, but somewhere between there, depends how complex your initial expression is. Generally speaking, grade 12s, they're not really going to ask you anything more complex than an x squared and an x term. We don't really ask cubic first principle sorts of questions. I'm not saying that they can't, they definitely could, but like in general, it is a quadratic expression where you either only have one x that you need to substitute, or you'll have an x squared and an x and you have to substitute in both. Okay, so just bear that in mind. And there was something else I was going to... Oh, remember in these first questions, so the first principles question and then the question where you're asked to find the derivative using the rules and the formatting and all of that, notation is very important. Any of your teachers who have marked finals will tell you that on the memo, in the memo discussion, they specifically say deduct a mark for notation in these questions. So it's 1 mark, which doesn't seem like a lot, but obviously if you're losing 1 mark throughout your paper for different reasons, rounding, notation, I don't know, not leaving a positive exponent when you're told to leave your answers with positive exponents, whatever, like silly little things, they all add up. So don't make the mistake. All right, so first principles. Obviously, we need to know our rule or our formula, which I did write down earlier, but first derivative of the function f is equal to your limit where h tends towards 0, 0, where f of x plus h plus, not plus, minus f of x divided by h. Now, grade 12s, I've said this to you before. If you are comfortable doing everything in one go, go for it. But my advice is don't. Go step by step. Okay? So there's no need to try and mush everything together and overcomplicate things. Just go step by step. So when I say go step by step, the first step that you want to complete is to substitute in or find the expression f of x plus h. So what this means is you want to take your original f of x expression, and every time you see an x, you want to replace that with x plus h. So we will have 2 minus 3 times x plus h squared, and then we go and simplify that. So 2 minus 3, we square our brackets, x squared plus 2xh plus h squared, and we distribute in that negative 3. Don't forget the 2, it's still there. Minus 3x squared plus 6x, not plus, minus. Okay, don't get signs wrong like I'm doing. Minus 6xh minus 3h squared. Okay. Once you've got f of x, then you can substitute into your formula. Minus 3h squared. Okay, cool. So now we're going to go back to our formula and we're going to substitute in. This is where the notation is really important. So we start with our derivative notation equals our lim h's to 0. And from this point, guys, each step you can just say equals lim h's to 0 and the rest of your working out. You don't need to put that derivative thing every single time. You'll put it at the end again. It's up to you. Right, so now we substitute in according to our formula. F of x plus h is this expression that we've just found. So 2 minus 3x squared minus 6xh minus 3h squared minus the original expression 2 minus 3x squared. That is all over h. We would distribute that negative in. If you can see what terms are going to cancel from this point, you don't really need to show the distribution. I'm going to, just so that we can see which like terms cancel. But like I say, if you can see it, you don't need to go and distribute in the negative and all of that stuff. You can just go straight to the simplified answer. All over h. And hopefully what we can see from this point is that the positive 3x squared and the negative 3x squared become 0. The negative 2 and the positive 2 become 0. Now, grade 12s, I've said this before. This should always happen. This f of x expression should cancel. Those terms should cancel away. If they don't, you have done something wrong. And the likelihood is that you've done something wrong in your distribution. Right, so what we now have, remember your notation, so keep your lim h's to 0 here, is minus 6xh minus 3h squared all over h. Your next step is now to factorize. Now, guys, obviously there's more common in your numerator than just h, but we only care about taking out h as a common factor so that we can divide away the denominator. So there's no reason to take out more than an h. Just take out h as your common factor, leaving you with minus 6x minus 3h And again, hopefully what we see is that this results in, like I say, those h's dividing away. We don't want them. Okay, we don't need them. Right, I'm going to carry on up here. Again, equals lim h is to 0, and we have an expression of minus 6x minus 3h. This is now where we will replace that h with a 0, because that is what h tends towards. Remember, the limits. And when we substitute in that 0, obviously negative 3 times 0 is still 0. And so we end up, once we substituted in that h is 0, with our derivative expression. Now, grade 12s, remember that you know the shortcuts. So you should be, when you see this question, immediately saying, okay, cool, 2 derives to 0, times the exponent by negative 3, negative 6, x exponent minus 1. You should already know what your answer should be. You then go and follow your first principles method in order to get that answer. But you should know what it is because you have the shortcut rules. Right, mark allocation. I always forget. Get in there. I know I did relatively well this time. So mark allocation, you're going to get a mark for determining your f of x plus h, whether you do that separately or in the expression, whatever. You get a mark for substituting into the derivative formula. And again, guys, just, distribute. I mean, you saw when I was doing that there, the mistake we often make is in the distribution. We forget a negative, we forget my coefficient that I kept forgetting. Those are the mistakes that we often make when we are doing this. So just, don't make a mistake when you distribute, because you'll kick yourself. And like I said, those are not mistakes we want to be making. All right, anyways, so what have we got? We've got the f of x plus h. Like I say, whether you do that separately or in the formula, you do you. It's your choice at the end of the day. And we get our substitutes into the formula. Right, you then get a mark for simplifying. So essentially getting to a point of minus 6, that thing, simplifying. You get a mark for doing your factorization step. And then your final 5th mark is for the answer. Like I say, there will be a subtraction for notation. So notation things are things like not putting these h's to 0 or putting them on the wrong side of the equal sign, etc., etc., etc. Those are notation issues, and that will lose you a mark at the end of the day. Now, because this formula is on your formula sheet, there is no excuse for you to be losing those marks. You're literally copying it down exactly as it is on your formula sheet. So like I say, no excuse to lose those marks. Yeah, that is 5 marks. Lorato?
Ma'am, so is it okay for me, because I rearranged the formula when I was trying to solve for f of x plus h. So I just put it as negative 3x squared plus 2 and then just substituted the x plus h. But then I also got the long equation that you got for number 1.
Okay.
It's just that my 2 is at the end.
Sorry, okay. I don't know. My brain didn't compute that. What did you rearrange? How did you rearrange?
The f of x formula. So I said it's negative 3x squared plus 2. Basically swap the 2 around.
Oh, gosh.
Yes.
See, my brain wasn't computing. Yeah, that's fine. That's okay.
Okay. And then, ma'am, with the lim h to 0, basically, would you lose a mark if you didn't write it when you were substituting the 0 into the h, basically?
You don't really have to show that substitution step. Obviously, you can if you want to. But no, because you're showing that limit is h's to 0. So no, it would be fine. Okay. Sorry, I don't know why it took me so long to compute the reorganizing. Jeez. Anywho. Okay. I was so confused. I was looking like within the formula, and okay, but I'm there now. I'm on the same page as you. I'm there. Okay. Sorry, guys. Let's take a screenshot of this, and then let's have a look at the questions where now we have to apply our rules. Right, now again with this one, notation really important, using the correct notation, correct formatting, etc., etc. So it says determine first derivative of f if f of x is equal to x to the power 4 over 2 plus x to the power 0 minus pi t squared. Now, firstly, guys, what should be throwing you off is the pi t squared. Pi is a number, so that's a constant. That's like saying 3t squared, 5t squared, negative 2t squared, whatever. Pi is a number, so that is a coefficient. We don't need to stress about that. What often throws us is when we do chuck in a random variable. And what you need to do is you need to go back to what the questions actually asked you to do. This question has asked me to find the derivative of this expression in terms of x. So whenever we chuck in a random variable there, that is ignored. We treat it as a constant. So essentially, this whole last term here, we treat as a constant because I'm not finding the derivative in terms of t. So I don't actually care about t. Okay, so we treat it as a constant. Now, a couple things. My advice, and particularly because fractions aren't always our favorite thing, is if we give you the fraction with your variables in the numerator, just separate it out. So write this as a half x to the power 4. Obviously, if you can see that and you know that's what it represents, great, that's awesome. But like I say, don't overcomplicate the situation if you struggle with fractions. I always do it like this, otherwise my brain doesn't compute. As we see earlier, it has a problem sometimes. We know that x to the power 0 is 1. And like I say, technically this is a constant. So we can just keep it as it is. We're not too concerned about it. So get your formatting right before you do anything else. Once our formatting is correct, we can now go to the derivative. And what I want you to see is that I haven't yet used derivative notation. This expression that I've written down is still f of x. We only start using the derivative notation when we plan on start applying our rules. So now I'm going to apply my rules. We know that we take the exponent and we multiply it by the coefficient. So 4 times a half is 2. And then from that exponent, we subtract 1. So 4 minus 1 gives me an exponent of 3. Because both of these are constants, that just derives to 0, which obviously you don't need to write. And so we get that the derivative of f of x is equal to 2x cubed. That's it. Right? Now, this was only a 2 marker, so it shouldn't have been too tricky. And essentially, your marks are being allocated for your answer. So getting the 2x cubed and essentially getting a plus 0 here. So you don't have to show the plus 0. You don't have to write it. But you need to understand, or you need to make very clear that you know that the derivative of a constant is 0. So you don't have to show plus 0, but you do need to be very clear that there's no constant there. Kani?
Ma'am, can you please explain again why the pi is referred to as a constant?
The pi specifically, or the negative pi t squared, the whole term?
The whole term.
Okay, cool. So, like I said earlier, sorry, let's just do this. So pi is a number. We just use a symbol to represent it because it is irrational, continuous whatever. So this is a number. And because t is not what I'm looking for the derivative of. So if this had said the derivative of f of t, then I'd be finding the derivative in terms of t. But it says the derivative of f in terms of x, f prime x. Because that variable t is not the variable that we are concerned with, we treat it as just a constant. Because we don't care about what that specific variable's derivative is, we treat it like a constant. But like I say, if I had said find the first derivative of t, then I would be ignoring the x's and then I'd be finding the derivative of that term with the t in it. So that's what I'm saying. It's very important for you to look at what variable you're actually working with, because it does change the way you find your derivative. But like I say, because t is not the variable I'm concerned with, we just treat it like a constant and it derives to 0. If, however, this had been pi t squared x, for example, because it would then contain an x, I would still then need to find the derivative of that. So then that x is an exponent of 1. 1 times my coefficient is just pi t squared minus 1 x to the power of 0. So that would then derive to that. So if there was an x, we would need to consider it, but because there's no x, we don't really care. So like I say, whenever there's a variable, yeah?
If the question had said, like, find the derivative in terms of t, then would we take the a half x to the power of 4 and make that a constant?
Exactly.
Oh,
Well done.
okay.
Exactly.
Thank you.
Good. Lorato?
Ma'am, I just have a few questions. So, if it was asking to find the derivative of t, would it basically be 2 pi? Then,
Yeah, minus 2 pi t.
okay. So we don't have to now in our calculator say 2 times 3,14. It's just 2 pi.
No. Just keep the pi. Yeah.
Okay. And then I wanted to ask, ma'am, if you don't mind, when you were moving from the x to the power 4 divided by 2 into a separate fraction, would it also apply if it was a 2, maybe for example, if the question had said 2x cubed divided by 3, so would it be 2 over 3 times x cubed?
Yes, exactly.
Oh, okay.
So as long as your variable's in the numerator, you quite literally just separate it out and you can write it separately like that.
Okay, thank you, ma'am.
Pleasure. Layla, sorry, I did see your question. I'm assuming this is what you're going to ask me now. Layla, the previous first principles one.
No, I'm actually wanted to ask a question about this as
Okay.
well. So a double type of question. Ma'am, so I wanted to ask, with this one that you just did, is it possible for them to ask us to find the derivative of x and t in the same equation?
No, because the variables would represent different values. So you'd then be deriving two different things. So no, it would specify which variable.
Okay, ma'am, and is leaving t out, like as in treating the pi t squared thing as a constant, it doesn't affect our derivative at all because we're looking for the derivative of x?
Exactly. Like I said, the only time it would have affected it is if this term had been minus pi t squared x. Then because there's an x, we would have to then find the derivative of that term. But because there is no x, like you say, has no effect.
Okay, thank you, ma'am.
Okay. Sorry, which one do I have to scroll back to? The first principle one?
Ma'am, just to the first principle one. I was having network issues.
No, that's fine. There we go.
Thank you so much, ma'am.
Okay, so guys, again, kind of what everyone said, if it doesn't say the variable t or x or r or whatever, you find it in terms of the variable you've been given and you just ignore the rest. Okay, I did do my mark allocation. Sometimes I know what I'm doing, sometimes I don't. Okay, so 6.2.2, this is a derivative notation that we often ask, okay? The derivative notations that we often ask are the f prime, the d of x, and the dy over dx. There are other notations, but these are the ones we use most. Okay. And we did do a summary in class of all of the notation things, so you can go and have a look at those recordings if you want. All right, so this one is a fun one because there is a variable in the denominator, there is a root, and we need to simplify. So all of the things that we said we need to sort of bear in mind, we have to do this here. Now, again, grade 12s, we do not use derivative notation until we are finding the derivative. Now, the notation with this situation of the dx and then the square brackets is that this is telling me to find the derivative of whatever expression I put in those brackets. The second I find the derivative, I'm just going to write the expression. I drop the brackets, I drop the d of x, and I just write the derivative. So I need to keep these brackets and that notation until I find the derivative. And like I said, we first have to deal with a few things before we can do that. Now, again, grade 12s, this is going to go back to how comfortable you are with exponents and such. I'm going to drag out my working out just so that we're all clear. But obviously, if you're comfortable, you don't need to go step by step like I'm about to do. So the first thing I'm going to do is I'm going to deal with that surd, because I know to simplify this expression, I'm going to eventually have to separate each term in my numerator to be divided by x squared so that I can simplify each term. So the minus 3x cubed I have no issue with, but this 5th root of x squared I do. Now, I don't know if you remember me explaining this, but I always remember it as it's x to the power of whatever it was originally to the power of over the root. The root is at the bottom of a plant. It's at the bottom of the fraction. So this is written as x to the power 2 over 5 all over x squared. So we've dealt with the third. And now we need to deal with the simplification variable and the exponent thing. We cannot just bring that x squared up, okay? There's multiple terms in my numerator. I can't just bring it up. If there was one term in my numerator, awesome, bring it up to your heart's content, but we can't. In order for us to simplify this, we have to separate out the fraction. So we will have minus 3x cubed over x squared plus x to the power 2 over 5 over x squared. And now we go and simplify. As you can see, my notation is also there. I haven't even started finding the derivative yet. I'm still sorting out my formatting. So when I simplify this first term, 2 x's in the denominator cancel with 2 x's at the top, leaving me with just a minus 3x. And then remember, your exponent laws say that you subtract exponents when you divide. So this x to the power 2 over 5 divided by x squared, according to exponent laws, would be x to the power 2 over 5 minus 2. That's the subtraction law that we know from grade 8. So we need to go and subtract those two exponents. So it'll be x to the power negative 8 over 5. And even though that's a gross exponent, my format is now fine. Now I'm fine with everything that I have. Now I can find my derivative. So because I'm now going into my derivative, this is where I can drop the square brackets, the dx, I can drop all of that, and now I apply my rules. So remember, this x has an exponent of 1. Multiply that by the coefficient, so 1 times negative 3 is just negative 3. Subtract 1 from that exponent would leave me with x to the power 0, which is then just negative 3 times 1. So we just keep it as negative 3. Move on to a second term. We take this exponent multiplied by the coefficient, which is positive 1, and you get negative 8 over 5. X, subtract 1 from your exponent. Whoops. And you get x to the power negative 13 over 5. Not a nice situation, but we have found the derivative. That's it. You stop. Okay? Yes, you absolutely can take that rational exponent and start working with x to the power negative 13 fifth rooted. But remember, we've said that in calculus, I don't care. I don't care that your answer has a negative exponent. We only care about positive exponents in that very first question in paper 1, which is the algebra. But when it comes to calculus and these sorts of questions, I don't care about the negative exponent. Leave it. You're probably going to make some weird mistakes if you try and change it. The mark allocation doesn't even apply to changing it. I will show you what it will look like if you wanted to take that rational exponent and convert it to a surd, but we don't care. Just leave it as it is. Right, so your mark allocation here, you get a mark for understanding the rational exponents, the x to the power 2 over 5. You get a mark for, how many marks is this? 4. You get a mark for, someone screwed up, simplifying the first term. No, you don't. Sorry, I'm lying to you. Please ignore what I said. You get a mark for simplifying the second term, so x to the power negative 8 over 5, because that's a more complex simplification, essentially simplifying, okay? And then you get a mark for the derivative of your first term, the mark for the derivative of your second term. Okay, so the formatting is really important because that's half of your marks. If you screw that up, then you've lost half your marks. I feel like I said I was going to say something and now I don't. Oh, I said I was going to show you what the irrational exponent situation is. So if you really felt that way inclined and you felt very strongly about leaving all your answers with positive exponents, that's cool. This would become negative 8 over 5. Now, this exponent only applies to the x. Again, your denominator is your root. So this would be 8 over 5 to the 5th root of x to the negative 13. And if you really wanted to go a step further, it would be negative 3 minus 8 over 5 times the 5th root of 1 over x to the power 13. Do you see why I'm saying just leave it? There is no point in trying to write all of that nonsense. Just leave it with a negative exponent. Like I say, we don't care in calculus. We care a little bit more in algebra, but in calculus, we do not care. Okay. So I don't actually know what we've taken screenshots of. I'm just living my life here. I don't think we've taken a screenshot of the first one, so I'm just going to do that so we can take a screenshot of those two. Lorato?
Ma'am, so if you had written the negative 3 minus x over 5 times x to the power of negative 13 over 5 as just a normal step, but then you did your final answer as like one of the, basically the gray thingies, and you made a mistake, maybe like with your roots, would you get the marks for saying the negative 3?
Probably.
Because ma'am, it is there, but you just didn't indicate it's your final answer.
So I know I would probably give it. I'm going to be honest. I don't know what they would do in finals. I feel like they would probably give it to you. Technically, though, we mark your last thing as your final answer. So technically, we would have to mark it as your thing. But I feel like they would probably give it to you. But that's what I'm saying. Don't even risk it. Just stop with the negative exponent.
Okay. Thank you, ma'am.
Okay. Sure. All right, guys. So let's have a look at this one. Now, this is like going back to grade 10, which is fun. So it's saying the derivative of the expression y in terms of x, so that's what that dy over the dx thing, derivative of expression y in terms of x, if y is equal to 8x cubed minus 125 over 2x minus 5. Now I'm going to throw it out there for you what you need to do. We're going to see how many of you remember how to do this. So remember I said to you that we never want variables in the denominator and we need to simplify. I can't just split this fraction because I've got two terms in my denominator. So now we need to go back to factorization. And this is going to now call upon some knowledge of how to factorize the sum and the difference of cubes. And you're probably hearing this and you're like, oh, yeah, I remember that, but I can't remember how to do it. So I'm going to give you 2 minutes to muddle, to try and figure it out. You have to factorize the difference of cubes here. If you remember it, well done you. I'm going to be honest, this is one method of factorization that I sometimes struggle to remember. But we need to factorize this difference of cubes. Let's see what you come up with. So I'll give you 2 minutes. We'll see if we come up with anything. Like I said, I'm not expecting you to remember because I do understand it's grade 10 work. But it is part of your syllabus and matric, so you do need to know it. So let's see if we remember. Let's see what we come up with, and then we'll go from there. But I'm going to give you 2 minutes to, I don't know, problem solve, figure it out, troubleshoot, trial and error, see what you come up with. And if you do come up with something, you can pop it in the chat and we can see what we get. Very, very nice. We got a perfect derivative there. Well done. All right. So first question, and you can just give me a thumbs up, thumbs down. Does anyone actually remember how to factorize cubics? Or like, no, let's rephrase that. Does anyone remember how to factorize the sum and difference of cubes? I know, Kani, I agree. All right, so that's the thing, right? We kind of do it in grade 10 and then we never do it again. And then obviously in Mpumalanga, I think it was this year, this was their June paper this year, they decided, you know what? Let's throw caution to the wind and let's give this to them. So quick recap of factorizing those. So you either get the sum of cubes or you get the difference of cubes. Now, when it comes to cubic expressions of the ax cubed plus bx squared plus cx plus d, we've spoken about how to factorize that. Synthetic division or factor remainder theorem. And you decide. But when it comes to just two perfect cube terms that are either being added or subtracted to each other, there is a method that we can use. So one thing I always remember is that I'm going to end up with a binomial bracket and a trinomial bracket. And in one of those brackets, I need one negative sign. Okay, so sum of cubes, when we factorize this, the binomial bracket will be the sum of the cube roots of both of those terms. So to get x, I cube root x cubed. To get y, I cube root y cubed. And then my binomial term is going to be a plus minus situation. Oh gosh, now I'm panicking. It's not going to be a plus minus situation. It's going to be a minus plus situation. See, we panic. Okay. Oh, come on, you Lana. Right, minus plus. I do apologize. Panic moment. I recovered. Okay. Oh, I didn't recover because the minus disappeared. Recovered. So in order to get my binomial bracket, I take the first term of my binomial. Oh, let's try this again. The first term of my trinomial bracket, I take the first term of the binomial, square it. To get the last term, take the last term, square it. So x squared, y squared. I know it looks hideous, but we're just going to roll with it. To get the middle term, I take these two terms in my binomial bracket and I multiply them together. Now, yes, positive x times positive y is positive xy, but we know that we need the negative there, so it's a negative xy. We do exactly the same method for difference, except now your minus sign goes in the binomial bracket and the trinomial bracket will be plus plus. And that's how you factorize cubics. Or no, the sum or difference of cubes. Okay, like I said, grade 10, it's a while ago. Oh, Zavoyo, nice. I'm liking that expression. So if you have a look at Zavoyo's comment on the chat, that is the factorized situation we want. So y is equal to 2x minus 5. Now the hint here is obviously we want that denominator to cancel. So one of my brackets needs to be 2x minus 5. Cube root of 8x cubed, 2x, cube root of 125, 5. There it is. And because it's a difference of cubes, the minus sign goes in the binomial bracket. Square 2x, that's 4x squared. I've already got my negative sign, so it's going to be two positives in this bracket. The last term will be 5 squared, which is 25. And then I multiply 2x and 5 to give me 10x. All over my 2x minus 5. And obviously, like I said, the goal is to get rid of that fraction. So we should kind of get the hint that that should cancel. And so now we have y is equal to that quadratic. Now remember, these quadratic expressions can only be factorized using the formula. Obviously, we don't want to factorize. We're not trying to solve for x. We're fine with what we have here, but just as like a tangential reminder. Right, now we go and find the derivative. Again, notice my notation. I have not introduced any derivative notation until I'm about to find the derivative. So now I can say, therefore, my derivative is equal to, and now I just apply my rules. So I take my exponent multiplied by my coefficient. and then subtract 1. So I get 8x. Same thing for my second term. Take my exponent of 1, multiply it by the coefficient, subtract 1 from the exponent. So I end up with just 10 because x to the power 0 is 1. And obviously that 25 is constant, so it falls away. So my derivative is 8x plus 10. Right, in terms of your mark allocation for this specific question, obviously the whole factorization journey we went on is going to be worth a mark. It's only worth 1 mark, so you factorize the simplified answer and then the derivative. So oftentimes when we are expecting a bit of working out, obviously we're going to allocate marks accordingly for you. Lorato?
Ma'am, would the 2x minus 5 bracket still cancel out if, let's say, the denominator was a 2x plus 5 instead of a
No, they
2x?
have to be identical.
Okay. And then I wanted to ask, so if it was a dx over dy, would it have to be like an equation whereby there's y variables within the formula?
Yeah, so dx over dy would be something like x is equal to, I don't know, y squared plus 4y minus 7. And then you would find the derivative of the x expression in terms of the y variable.
Okay, so here we're finding the y expression in terms of x.
Yes, exactly.
Okay.
Yes.
Thank you, ma'am.
Sure. All right, guys, I'm just going to wait for you to screenshot this last little bit. I know we've taken a screenshot of the one before. I'm going to tell you now we're not going to get through the whole of question 7, but that's absolutely fine. Maybe I'm going to make a choice. I'm going to go rogue. We're going to give you some to practice by yourselves, seeing as we've had this conversation, and then we'll talk about cubics on Wednesday. Okay. I'm my own chaos, truly. Right, I'm assuming we screenshot. So I am going to ask you to try these two by yourselves. Okay. So there were some words I was going to use. Obviously now I can't really remember what all of those words were. But anyways, so we're going to try these two. I remember my words. It's worth 7 marks. So technically 7 minutes, but let's see how we go. Give these a try. Remember, no variables in the denominator, no surds. We need to simplify as far as possible. And hopefully what you can see is that there in question B2, that's another whole difference of cubes situation that we have in that first bracket. So hint, hint, nudge, nudge, what we've just done is probably going to be useful to you. Okay, so let's give it a try. If you have questions as you go along, just ask. You can unmute yourself. You can put it in the chat, whatever. But let's try these two.
Ma'am, what's the expression on the first one?
Is it just too small?
Yeah.
Is that better?
A little bit bigger, please.
Okay. It's this fraction. There we go. Is that better?
Yeah, it's better. Thank you.
Okay, cool. I'm going to make this one bigger as well, actually. Okay. Absolutely, you're more than welcome to. Let's see what's happening. Okay, guys, out of interest, give me a thumbs up if you're done. Like, I'm fully aware of the fact that you might need more time, and that's absolutely fine. Okay, we're kind of half and half. I think how best to do this, because obviously I know that some of you need to go at 7 o'clock. All right, so what I'm going to do is I'm not going to do the answers. I'll put the answers up. Okay, it seems like most of us are done. All right, so I'm going to do the answers. If you're not done, don't stress. You'll catch it up. Just because now it's more I'll come in and it seems like we're okay. All right, so firstly, we need to get our formatting correct for this one. So again, if you can do everything all in one go, that's awesome. If you can't, that's also okay. So this would be x cubed plus x 3 over 2, or to the power 3 over 2, excuse me, over x. And then we'd separate our fraction. So x cubed over x plus x to the power 3 over 2 over x. And then we simplify. So y is, sorry, okay, let's see what the issue is. I might just need to reshare. Okay, let me know if you can see the screen now. Okay, cool. All right, so simplify x squared plus, now remember we subtract the denominator, so it'd be 1.5 minus the exponent 1, so x to the power half. Now we can find the derivative. So the derivative of this expression would be equal to 2x plus a half x to the negative a half. Again, don't try and deal with that negative exponent. There's no reason to do that. We are perfectly fine with you just leaving it with the negative exponent. There's nothing wrong with that. Just fix that denominator because that was gross. Kanya, I saw your hand. No, maybe I didn't see your hand. Did I see your hand? Am I seeing things? Oh, okay, cool. Just question my sanity for a second there, which is always fun. All right, so like I said, leave the negative exponent. There's no reason to do anything with that. Okay, this bad boy over here, we need to simplify the situation. Now, the key thing here is that you've got a negative exponent. So we know negative exponent means we can create a fraction. So that's the first thing I'm going to do. I'm going to leave the 8x cubed minus 27 in my numerator. And I'm going to put that quadratic in my denominator. And like I said, when I asked you to try this, you need to go back to the difference of cubes. So when we factorize this difference of cubes, we get 2x minus 3. Yes, 2x minus 3, sorry, panic. 4x squared plus 6x plus 9, all over that same quadratic. 4x squared plus 6x plus 9. Now, Gary tells us it seems like a really silly statement, but if you want to put your denominator in brackets, that's absolutely fine. I prefer to do that so that I know I have to cancel out the whole bracket. I can't just cancel out individual terms. It has to be the entire bracket. Again, seems like a silly statement, but often, for whatever reason, we like to just start dividing away things that we shouldn't be dividing away. So I'm looking for the derivative of the expression 2x minus 3. And so now, because I am actually finding the derivative, I can drop the notation, and I just get that my derivative is 2. Okay, the negative 3 is a constant, falls away. The 2x, I would take the exponent of x, which is 1, times it by the coefficient 2, subtract 1, I'm just left with 2. Right, so the key thing here was obviously the factorization. I know you're going to ask me about mark allocation. So, simplifying both of the terms appropriately in the first one, and then deriving both of the terms appropriately in the second one. In the third one, factorizing, getting the appropriate simplified expression, factorizing to 2. Those are your 7 marks here. All right, so guys, like I said, like the key thing here is just your ability to get the formatting correct. Once the formatting is correct, you just apply the rules and you go. All right, so I will just wait in case you want to take screenshots of those two. I am aware of the fact that it's 3 minutes past 7, so if you need to go, that's absolutely fine. I will see you on Wednesday.